I'm excited to have the opportunity to present on the fascinating interplay between the Kelly criterion and game theory. The Kelly criterion provides a mathematical framework for making optimal investment decisions by determining the ideal percentage of wealth to wager on a given opportunity when there are infinite bets. It aims to maximize the expected logarithm of wealth, so it is particularly relevant in contexts where continuous reinvestment is allowed. Meanwhile, game theory explores the strategic interactions between players in competitive scenarios, helping us understand how decisions impact outcomes based on the action of others. Together, these concepts empower us to make informed, calculated choices in finance, sports, and everyday life. Today, my presentation will focus on decision-making and competition. Learning to be an effective decision maker is crucial when faced with various options in life. The goal of a reasonable decision maker is to identify and seize opportunities with a positive expected value while ignoring decisions with a non-positive expected value. To make an optimal decision, we need to calculate the optimal percentage of effort to invest in each opportunity, given that our time and capital are limited. We can achieve this by estimating the odds and the probability of achieving the desired result for each decision, as nothing in life is certain. Now, we understand how to make reasonable or optimal decisions. Let's talk about competition, as real-life scenarios are often competitive by nature. Competition shifts our focus from absolute performance to relative performance. The main goal in a competitive setting is to outperform your competitors. A key component of winning in competition is to fully understand your opponents. In the following presentation, we will demonstrate the importance of knowing your opponents and how will this knowledge enhance our decision-making process in competitive situations. Let's say you find an option trading opportunity that appears vastly undervalued. Based on your analysis, this option has a 10% chance of increasing in value by 100 times, while there is a 90% chance it will go to zero. It seems like a no-brainer buy, given the high expected value. However, here is the dilemma. With a 90% of chance, the value is going to zero, assuming your probability estimation is accurate. This raises an important question. How should one allocate his or her assets to avoid betting too little, thereby missing out on meaningful gains, while also not risking too much and jeopardizing capital for future investment in case of a loss? How would you approach this decision? You might have some questions related to the previous slide. For example, how often will this opportunity arise? Do I have additional cash flow? What is the investment horizon? These are crucial questions to consider before making any investment decision and can relate it to many aspects of decision-making in life. Let's assume that all future cash flows are linked exclusively to the outcome of this specific trading opportunity. The risk-free interest rate is 0%. The trading size can be infinitely divisible, and you have an infinite number of opportunities to determine your trading size for each round. Furthermore, the goal is to find the optimal strategy to maximize your wealth after an infinite number of decisions. How are you going to approach it? The optimal betting size each time for the question we mentioned in the previous slide is 9.1% of your current wealth. This calculation is based on the formula derived by Edward Thorpe in 1984, which formulates the Kelly criterion. The formula is F equals P minus open parentheses 1 minus P close parenthesis divided by B. In this formula, F represents the optimal fraction of your current wealth that you should bet according to the Kelly criterion. P is the winning percentage or the probability of winning the bet, which range from 0 to 1. 1 minus P indicates the probability of losing the bet. B denotes the odds of the bet, showing how much you will win relative to your stake. The Kelly criterion helps us determine the optimal amount to wager based on our assessment of the winning probability and the odds, allowing us to maximize our expected wealth over an infinite number of decisions. While the Kelly criterion provides us with an optimal strategy for scenarios where we can make an infinite number of choices, but in real-life situations, both in business and personal contexts, we often encounter competition characterized by a finite number of decisions and limited time frames. In light of this, we will shift our focus from pursuing absolute performance to understanding relative performance, essentially how we measure success compared to others. Let's consider the difference between absolute performance and competition. In a competitive scenario, when you know you have an edge over your opponent, you can adopt a more conservative approach to preserve that advantage. The position is often more advantageous because it minimizes risk while maximizing your potential to outperform other competitors. Conversely, if you perceive yourself as disadvantaged, you may need to take bolder risks to improve your chance of success. In such cases, being willing to take calculated risk can help you level the playing field and potentially overcome your competitors. Within this framework, we define a game as a structured competition in which opposing parties strive to outperform one another according to specific rules and conditions. Game theory has emerged as a critical area of study, providing valuable insights into how participants' decisions lead to various outcomes and how to adapt to others' reactions. By engaging with game theory, we also equip ourselves with the necessary insight to analyze strategic interactions and effectively navigate the complexity of competitive environments. Before the development of what we consider game theory today, ancient cultures had already recognized the importance of understanding one's opponents and oneself in strategy, a notion famously highlighted in The Art of War, a text from 5th century BC. Knowing the other and knowing oneself. In 100 battles, there's no defeat. This idea illustrates that long before the field of game theory as we know it, people understood how strategy could shift when one holds an informational advantage. Modern game theory, as formalized by John von Neumann and Oskar Morgenstern in 1944 in their groundbreaking work, Theory of Games and Economic Behavior, introduced the concept of several rational players with conflicting interests. Today, we characterize games by horizon and informational type. Some games have a finite horizon, like chess, where each move has a clear endpoint. Others, such as infinitely repeated betting games discussed in Edward Thorp's 1984 paper, have an infinite horizon. When an additional player is introduced in these betting scenarios, they become competitive games, as described by modern game theory. We can also classify games by move order and information completeness. In simultaneous move game like rock, paper, scissors, players act without knowing the opponent's choice. In contrast, sequential games, such as chess, allow each player to see the previous move. Lastly, we distinguish between games of complete information, like chess, where all elements are known, and games of incomplete information, such as poker, where some information remains hidden. This distinction set up the strategic landscape we will explore later. To explore the application of the Kelly criterion in competitive scenarios, together with game theory, we will examine both finite and infinite horizons. We introduce a game called Jack Tons Challenge. In this game, each player decides how much to invest in each round of an N-round trading game, where N can be finite or infinite. The goal of the game is to maximize the probability of outperforming the other player after the N-round trading game is concluded. To formulate the game, we define key parameters. The winning probability for each round is denoted as P. The odds are expressed as B to 1. Importantly, the condition PB must be greater than 1, ensuring that the Kelly criterion indicates a non-zero investment, and the game has the potential for positive expected returns. For this presentation, we only focus on the two-player games of Tze Chen's challenge, Party A versus Party B. We will consider two distinct modes of play. Mode 1. Party A is unaware of the results of Party B's previous investments and results. This introduces uncertainty, as Party A must make decisions without visibility into Party B's strategy or outcomes. Mode 2. Party A knows the result of Party B's previous investments and results. This additional information can significantly influence Party A's strategy, allowing for more informed decision-making based on Party B's performance. By analyzing these two modes, we can explore how information impacts strategic decisions and outcomes in everyday competition. Let's explore why we introduce Tze Chen's challenge and its significance in context of game theory. First, this game allows us to investigate both finite and infinite cases, which is crucial for understanding how strategies differ across different horizons. By studying various lengths of play, we can appreciate how players might adjust their tactics based on specific circumstances they encounter. Next, we focus on relative performance. By doing so, we emphasize that players must consider not only their strategies, but also how these strategies are reasonable or optimal against their opponent's decisions and circumstances. This competitive dynamic is fundamental to many real-world scenarios, such as corporate strategy or competitive sports. Moreover, the game is easy to modify to fit real-world competitions and measure the value of various types of information. This flexibility makes it a versatile tool for analyzing strategic interactions across multiple fields. These concepts not only apply to theoretical scenarios, but also reflect real-world competitive dynamics, which we will explore further. Let's go over some examples of Tze Chen's challenge to better understand its dynamic and strategic implications. In this game, you play the role of Party A, starting with an initial capital of $100. Importantly, Party B also begins with initial capital of $100. Each round, you choose the percentage of your current wealth to invest. Meanwhile, Party B will follow the Kelly Criterion, which is the optimal investment size when the number of rounds tends to infinity. You have the option to choose between two modes. Mode 1. In this mode, you do not know any of Party B's previous results. Mode 2. Here, you are aware of all previous results from Party B. This setup introduces an interesting layer of strategy. Your decisions on how much to invest can be influenced by whether you are operating under uncertainty or have complete information about Party B's past performance. To add some excitement and uncertainty to the game, we generate the probability of winning and the odds using a simple Python function. The function creates a random probability between 0 and 1 and generates odds between 0 and 5. It ensures that the product of probability and the odds is greater than 1 to keep the game fair and engaging. This combination of strategic choices and uncertainty reflects the core concepts we discussed earlier about relative performance and the importance of understanding both your own and your opponent's strategies. As we move forward, we will delve into specific examples of how these strategies play out in practice. Now, let's look at the results of our example in Tze Chen's challenge. In this scenario, we conduct a one-round game. It is important to note that Mode 1 and Mode 2 do not impact the results in this case, as they are essentially the same. Because we are only playing one round, there is no historical data from earlier rounds to guide our decisions. Now, the Python code generates the winning probability and odds. The probability of winning is P equal to 80%, and the odds B is equal to 5. These values provide the foundation of our investment decisions. Next, let's consider the strategy that Party A is going to take. We see Party B use the Kelly criterion to determine their investment for round 1 based on the given probability of winning and the given odds, which lead them to invest 75.41% of their capital. For us, as Party A, however, the decision was made to invest 100% of our wealth, entering the game with our full capital. As a result of this decision, we find that after round 1, our new wealth increased to $600, while Party B ends up with $476.90. In this instance, we, as Party A, win. This example illustrates how strategic decision, influenced by the horizon of the game, the probability of winning, the odds, and the knowledge of other player strategies, can significantly impact outcomes in Jack Tong's challenge. We are going to discuss the potential reasons why Party A invests 100% of our capital on the next slide. In example 1, we, as Party A, decided to invest 100% of our wealth. This raises an important question. What are some potential reasons for this decision? Do you think this was a good move? I invite you to consider the rationale behind such a strategy and to potentially find other optimal investment percentages. Remember, this game is a one-round game. Next, let's dive into the discussion. Recall that Party B will invest based on the Kelly criterion, which is designed to maximize expected logarithm wealth over an infinite horizon. Since this is a one-round game, the outcome depends only on this single investment. Each party has a probability of winning this bet set at 80%. If we, as Party A, decide to invest more than the amount suggested by the Kelly criterion, then, based on conditional probability, we have an 80% chance to win if Party B invests the amounts according to the Kelly criterion. Therefore, the optimal decision for us would be to choose any real number greater than 75.41%, the investment percentage suggested by the Kelly criterion for this game, up to 100%. Let's consider a one-round game where we have two parties, Party A and Party B, each with an investment opportunity. In this scenario, the investment has a 30% chance of increasing 4 times in value and a 70% chance of going to zero. Our goal is to analyze the optimal strategies for both parties, where the objective of both is to maximize their chance of winning or achieving a tie against the opponent after the one-round game concluded. Let's also think about the outcome of the game. Now, let's generate some ideas to solve question 2 and analyze this game. First, it is important to recognize that this is a symmetric game. This means we can analyze the game from the perspective of Party A, and the optimal strategy for Party A would also be the best decision for Party B. In other words, the strategies are interchangeable because both parties face the same conditions and the exact same payoff structure. Next, by conditional probability, if Party A invests more than Party B, then Party A would face a 70% chance of losing the game. Because this game is a one-round game, we do not need to consider the odds. Instead, focusing solely on the probability of a successful investment is sufficient for this game. Therefore, Party A does not want to invest more than Party B. As a result, The optimal decision for Party A is to invest 0% of its capital. Since this game is symmetric, Party B will also make the same choice, leading to a scenario where both parties invest 0% of their capital, resulting in a 100% probability of ending the game as a tie game. Does this surprise you? From question 2, we can generalize our findings and arrive at Theorem 1. Theorem 1. When n is equal to 1 in Jack Tang's challenge, where both parties have the same probability, P, and odds, B. The optimal strategy is solely determined by the value of P. We can demonstrate this case with 3 cases. Case 1. When P is less than 50%. Case 2. P is greater than 50%. Case 3. P is equal to 50%. For case 1, if P is less than 50%, as we discussed in question 2, the optimal strategy for both Party A and Party B would be to invest 0% of their capital. This discussion guarantees a 100% chance of ending in a tie game, reflecting the same strategic insights we derived earlier. The reasoning behind this is exactly the same as question 2, so let's omit the detailed explanation here. Case 2. For probability greater than 50%, the optimal strategy for Party A and Party B is to bet all the wager. This is essentially the opposite of question 2. We can omit the proof of optimal strategy, but let's inspect the outcome of the game. First outcome, a tie game. The probability of a tie game occurs when both Party A and Party B achieve the same outcome regarding their investment. This can happen in 2 ways. First, both parties successfully achieve their desired investment outcome, which has a probability of P times P. Second, conversely, both parties could also incur a loss on their investment, which occurs with a probability of open parenthesis 1 minus P close parenthesis time open parenthesis 1 minus P close parenthesis. Adding this together, the overall probability of a tie game can be expressed with the formula P times P plus open parenthesis 1 minus P close parenthesis time open parenthesis 1 minus P close parenthesis. Second outcome, Party A win the game. For Party A to win the game, the conditions are as follows. Party A must successfully achieve a desirable investment outcome, which occurs with a probability of P. At the same time, Party B must incur a loss on their investment, which occurs with a probability of 1 minus P. Therefore, the probability of Party A winning the game can be represented by the formula P multiply open parenthesis 1 minus P close parenthesis. Third outcome, Party B win the game. Again, since this game is symmetric, Party B has the same probability of winning the game as Party A. This probability again is P multiply open parenthesis 1 minus P close parenthesis. The result of the game when probability of winning is greater than 50% are significantly different from those when probability of winning is less than 50%. Does this surprise you? Case 3. For probability equals 50%, in this scenario, every strategy will lead to the same result. But how? To explain, we can break it down this way. If Party A invests more than Party B, Party A will win if a successful trade happens. But since P is equal to 50%, Party A only has a 50% chance of winning this trade. On the other hand, if Party B invests more, Party B would win if their trade is successful, also with a 50% chance of winning. Now, let's think about the opposite side. Both parties also have a 50% chance of losing if the trade is unsuccessful and if they invest more than the other party. So, no matter how much each party invests, as long as P is equal to 50%, Each party has 50% to win and 50% to lose the game. Therefore, in this case, the game becomes random and without any strategic advantage, since no strategy provides a better outcome. Isn't that surprising? Do you think we missed anything? Probably you were thinking about a tie game. Continuing from the last slide, let's explore how this game will result in a tie game, and if that is even possible. For a tie game to occur, it is necessary that both party A and party B invest exactly the same amount. Additionally, they must get the same trading result, such as both party A and party B winning the trade, or both party A and party B losing the trade. Is this possible? Since the strategy does not matter, party A and party B will choose randomly from the interval 0 to 1. Mathematically, this interval contains infinitely many numbers. The probability of both parties selecting the same exact real number from this interval is infinitesimally small. Therefore, the probability of both parties investing the exact same amount is 0%. However, we say it is not technically impossible because, although the probability is 0, both party A and party B might unintentionally choose common numbers such as 0, 0.5, 1, or any other familiar value. We can extend our previous finding to Corollary 1.1. Recall that Jack Tong's challenge focuses on relative performance, that is, maximizing the probability of winning or reaching a tie game with the other player. Again, this is a two-person game. Corollary 1.1 states, when the round of the game n is equal to x, and there is no information about the other party's investment results, both parties, assuming identical probability of success, P, and odds, B, should adopt an all-capital investment strategy for each round if P raised to the power of x is greater than 1 over 2. This means that if the component probability remains above 50%, going all in is the optimal approach to increase the chance of winning or reaching a tie game. This builds on case 2 in theorem 1, but here we generalize it specifically for a finite round n equal to x, and no knowledge of others' previous results. Let's take a look at the opposite of Corollary 1.1. Under what circumstances should we adopt a zero investment strategy for all rounds? In Corollary 1.2, we explore this scenario in Jack Tong's challenge. We assume that n equal to x for both parties with the same probability of winning an investment, P, and the odds of the investment, B. The optimal strategy here is the zero investment approach for each round if 1 minus, open parenthesis, 1 minus P, close parenthesis, raised to the power of x, is less than 50%. This condition suggests that the probability of winning at least one round, meaning that the investment will turn out to be successful, is low enough that avoiding investment altogether is the best strategy. Now, let's think for a moment. What does 1 minus, open parenthesis, 1 minus P, close parenthesis, raised to the power of x mean in our context? Well, 1 minus, open parenthesis, 1 minus P, close parenthesis, raised to the power of x represent the probability of winning at least one round before the game is over, as the game only has x rounded. Here, open parenthesis, 1 minus P, close parenthesis, raised to the power of x gives the probability of losing in all x rounded, as 1 minus P is raised to the x power. By subtracting this expression from 1, we have the probability of winning at least once across all roundeds. In this situation, if that probability is less than 1 over 2, it implies a high likelihood of a cumulative loss, making the zero investment strategy across all rounds the optimal choice. We can prove Corollary 1.2 by showing that if you make a zero investment for 1, 2, 3, or even up to x rounds, you would have more than 50% chance of losing the game. Starting with the proof, let's define y as the number of rounds with non-zero investment. This number can range from 1 to x. The probability of winning at least one of these rounds is represented by 1 minus, open parenthesis, 1 minus p, close parenthesis, raised to the power of y. Now, observe the progression in the inequality. 1 minus, open parenthesis, 1 minus p, close parenthesis, is less than 1 minus, open parenthesis, 1 minus p, close parenthesis, raised to the power of 2, is less than 1 minus, open parenthesis, 1 minus p, close parenthesis, raised to the power of x, is less than 1 over 2. This progression shows that as long as you make a non-zero investment in any rounds or in multiple rounds up to x, the probability of winning at least one round remains less than 50%. In other words, this means there's more than 50% chance of losing money if you choose to invest. Therefore, the optimal strategy in this case is to avoid investing in every round. Why is this the best choice? Because if you refrain from investing and the other party does invest, you have over a 50% chance of winning the game without risking a loss. To summarize what corollary 1.1 and 1.2 imply, let's recall the key strategies each one suggests based on their specific conditions. As we discussed on the previous slide, corollary 1.1 applies when probability of winning each round, p, raised to the power of x, that is, the horizon of the game or the round of the game, is greater than 50%. It suggests an all-in investment for each round. In contrast, corollary 1.2 implies when 1 minus, open parenthesis, 1 minus p, close parenthesis, raised to the power of x is less than 50%. It recommends a zero investment strategy for each round. Here, the optimal choice is to avoid investing altogether, preserving capital by not participating in any rounds. These two strategies, an all-in approach versus no investment, highlight how the optimal strategy can shift significantly depending on the conditions of the game. When we compare this strategy to the Kelly Criterion, we noticed a clear divergence in recommended approaches. Recall that the Kelly Criterion suggests a non-zero proportionate best size when the product of probability and odds is greater than 0. Moreover, the Kelly Criterion doesn't recommend going all in unless probability of winning is 100%. However, corollary 1.1 suggests an all-in strategy under the condition that p does not necessarily equal to 100%, and corollary 1.2 recommends a zero investment strategies even if p multiplied by b is greater than 1. This comparison between Jack Tong's challenge strategies and the Kelly Criterion emphasizes how a competitive and finite game environment can lead to optimal strategies that differ significantly from Kelly's Criterion's approach. We just showcased the difference between the Kelly Criterion and Jack Tong's challenge under finite condition in the previous slide. Now, you're probably wondering, is there any direct connection between the Kelly Criterion and Jack Tong's challenge? Well, when the horizon of the game or the number of rounds of the game is infinite, this connection becomes clearer. This brings us to Theorem 2, which states, when n, the round of the game, tend to infinity, and there is no information about the results of previous investments, the optimal strategy for both parties, assuming they have the same probability of success in each investment, p, and the same odds, b, is to use the Kelly fraction for every round. The Kelly Criterion, as you may recall, is derived to maximize the infinite horizon expected geometric growth of the wealth in repeated independent investment. Theorem 2 shows that this result directly applies here because, with an infinite horizon and no dynamic change to P or B, the Kelly fraction remains the optimal strategy for both parties. Although this is a trivial case, it is an important theorem because it establishes a direct link between the Kelly Criterion and Jack Tong's challenge. It demonstrates how a classic result in financial mathematics can guide optimal decision-making in this specific context. Let's see if we extend corollary 1.1 to an infinite round game. We'll state this as corollary 2.1. When the round of the game tend to infinity, that is, n tend to infinity, and there is no information about the results of previous investments, the optimal strategy for Tze Chen challenge for both parties, assuming they have the same probability of success in each investment, P, and the same odds, B, for each investment, it is to adopt an all-capital investment strategy for every round, provided that P raised to the power of n is greater than 50%. This brings us to an important question. How does this infinite round case connect to the Kelly criterion, if any? Let's explore this further. Let's dive deeper into corollary 2.1 and its implication in both Tze Chen challenge and the Kelly criterion. We start by assuming P raised to the power of n is greater than 50%. As n tend to infinity, this condition implies P is equal to 100%. Why? Because if P is less than 1, then P raised to the power of n tend to 0, meaning the probability of success diminishes geometrically as the number of rounds increases. This result is fundamental to understanding the infinite horizon case in Tze Chen's challenge. Now, how does this align with the Kelly criterion? The Kelly criterion only recommends an all-in wager when the probability of winning is P equal to 100%. Edwards highlights the importance of not betting all-in unless the probability of winning is 100%. This insight underscores the significant risk of total loss when P is less than 1, especially in games with repeated rounds tending to infinity. Here is the takeaway. In Tze Chen's challenge, when the game horizon is infinite, the optimal strategy aligns with the Kelly criterion principle when P is equal to 100%. Otherwise, placing all-in wagers lead to significant risk in a repeated investing game with infinite rounds, underscoring the delicate interplay of probabilities and strategic planning in finite versus infinite games. Let's see if we extend corollary 1.2 to an infinite horizon game. When n tend to infinity, that is, the round of the game tend to infinity, and there is no information about other investment results. Corollary 2.2 suggests the optimal strategy in Tze Chen challenge for both parties, with the same probability of winning P and B odds, is to adopt a zero investment strategy in every round if 1 minus, open parenthesis, 1 minus P, close parenthesis, raised to the power of n is less than 50%. Does this suggestion align with the Kelly criterion? Let's discuss corollary 2.2 further by analyzing its implication. First, assume n tend to infinity, and that 1 minus, open parenthesis, 1 minus P, close parenthesis, raised to the power of n is less than 50%. Since P is the probability of winning, it must satisfy 0, less than or equal to P, less than or equal to 1. For this inequality to hold as n tend to infinity, we conclude that P equal to 0. If P is greater than 0, then open parenthesis 1 minus P, close parenthesis, raised to the power of n tend to 0. This further implies 1 minus, open parenthesis, 1 minus P, close parenthesis, raised to the power of n equal to 1. When the probability of winning is 0, both a rational person and the Kelly criterion would not suggest betting. In example 3.1, we explore Tze Chen's challenge in a two-round game. The parameters are as follows. The probability of winning a trade, P, is 30%, and the odds, B, is 4. Both Party A and Party B start with the same initial capital. However, Party A and Party B do not know each other's previous investment result or strategies. This lack of information makes the game more complex and adds a strategic layer to the decisions. Now, what is the main goal for both parties? Again, in Tze Chen challenge, it's not just about increasing their own capital, it is about maximizing the probability of finishing the game with equal or same capital than the other party. Every decision, and how much capital to invest and which round to invest is focused on achieving this goal. With only 2 rounds to play, this challenge becomes a fascinating exercise in balancing risk and strategy. Let's take a closer look at how they might approach it. Now, let's begin the discussion for example 3.1, where we analyze a case with n equal to 2, p equal to 30%, and b equal to 4. First, we calculate the probability of losing 2 rounds to see whether it is worth the risk to invest a non-zero amount in at least 1 round. The probability of losing a single round is 1 minus 30%, or 70%. Since there are 2 rounds, the probability of losing both rounds is 0.7 squared, or 49%. This means there's a 51% chance a party will win at least 1 round if they place a non-zero investment for both rounds. Second, let's address this important question. Could any strategy outperform a zero investment strategy over 2 rounds? While zero investment might seem like a safe choice, exploring other strategy could reveal better outcomes depending on the odds and other factors. Now, we can focus on the role of the odds. If the odds are sufficiently large, placing zero investment for both rounds may no longer be optimal. This underscores the importance of weighting potential risk against rewards when making decisions. We will continue examining example 3.1 in the next slides to analyze the outcomes after the first and second investments. Both parties have the same probability of success in a trade and the same odds, and both parties do not have any information about other party investment strategy or investment result. This game is symmetric. These symmetries allow us to analyze the game from the perspective of either party. For this example, let's assume the role of party A. Let's label the size of the investment for both rounds. We'll use D1 for the first round and D2 for the second round, where D stands for decision. Both D1 and D2 represent the percentage of the stake relative to the total wealth at the time the investment decision was made. In round 1, by the previous described probability of success, there is a 70% chance that the result is 1 minus D1, meaning the wealth decreased by the percentage of the first investment. On the other hand, there is a 30% that the result is 1 plus 4D2. 4 is the odds, meaning the wealth increased by 4 times the size of the second investment. After round 1, if party A ends up with 1 plus 4D1, then party A should make a zero investment for D2. This is because it is more likely to lose money in the second round. By avoiding excess risk, party A can maintain an edge in the competition. On the other hand, if party A ends up with 1 minus D1, then party A should make an all-in investment for D2. This is because the competition follows a winner-takes-all format. This demonstrates why, in certain competitive settings, participants take significant risk when the game is nearing its end. For example, think about a soccer match. When a team is lagging behind in the final minutes, the goalkeeper might even leave their goal to join the attack. While this decision significantly increased the risk of conceding another goal, the team takes this chance because the game's outcome depends entirely on scoring one more goal to equalize the game. This follows the same logic as taking an all-in approach when there's nothing to lose and everything to gain. Let's discuss further for example 3.1. As a quick reminder, we are working with n equal to 2, p equal to 30%, and b, the odd, equal to 4. In this case, we also assume 1 is the original capital. By our previously discussed strategy, for party A, there is a 30% probability to end up with 1 plus 4D1. Additionally, if party A ends up with the unfavorable results, 1 minus D1 in round 1, party A is going to bet all in round 2, as the odds are 4. This explains why there is a 21% probability to end up with 4 open parenthesis, 1 minus D1 close parenthesis. Now, we also need both investment sides to be effective for this strategy to work optimally. To find the balance, we set 1 plus 4d1 equal to 4 open parenthesis 1 minus d1 close parenthesis, and solving this gives us d1 equal to 3 over 8. With this strategy, party A would end up with capital is equal to 5 over 2 after the game. Finally, by using this strategy and assuming 1 is the original capital, party A has a 51% probability, which comes from adding 30% and 21%, to end up with more capital than the original after the game is over. Let's continue example 3.1. We claim the optimal strategy as follows. Party A choose D1 equal to 3 over 8. If party A wins in round 1, then D2 equal to 0, meaning no further investments are made. If party A loses in round 1, then D2 equal to 1, meaning all remaining capital is invested in round 2. Assume party A follows this claimed optimal strategy. Let's see if we can find a strategy that has a higher probability of beating party A. For this part of the analysis, we will take the role of party B. The hint is, party B adopts a strategy where D1 greater than 3 over 8. This strategy results in party B achieving a total probability of 64.3% to beat party A. This probability is broken down into two parts. 30% comes from party B winning in round 1 outright, and the remaining 34.3% comes from the scenario where party B loses in round 1, but still takes advantage of party A's strategy in round 2. So, how does this strategy work? Let's take a close look and think about how party B achieves a higher probability to beat party A. We will continue in the next slide. Assume party A follows our claimed optimal strategy. Now, let's analyze what happens if party B adopts the alternative strategy. In this strategy, party B chooses 1 greater than D1 greater than 3 over 8 and follows up with a 0 investment in round 2, regardless of whether it wins or loses in round 1. The probabilities for this strategy break down as follows. First, there's a 30% chance that party B wins the game outright by winning round 1. Second, there's a 70% chance that party B loses in round 1. However, party A has a significant 49% probability of returning to 0 after the game is concluded, while party B avoids returning to 0 entirely by investing nothing in round 2. This scenario gives party B a winning probability of 70% times 49%, which is 34.3%. Adding this probability together, 30% from the first scenario and 34.3% from the second scenario, party B achieves a total winning probability of 64.3% against party A. As the alternative strategy is more likely to beat our claimed optimal strategy, our claimed optimal strategy is clearly not optimal, but only reasonable. The key question now is this alternative strategy truly optimal? Let's think about this. Let's analyze what happens if one party places 0 investment in both rounds. We'll call this the always 0 strategy. This strategy has a 70% chance of beating the alternative strategy because there is a 70% chance that the alternative strategy will lose money. Now, let's look at the key results from this setup. The claimed optimal strategy beats the always 0 strategy. The alternative strategy beats the claimed optimal strategy. And finally, the always 0 strategy beats the alternative strategy. Notice the dynamic here. It is similar to the game of rock, paper, scissors. Each strategy beats one and is beaten by another, creating a cyclical advantage. While these 3 strategies are reasonable in this game, none of them can truly be considered optimal. This brings us the key question. Can we discover an optimal strategy for example 3.1? This might be a great computational game theory problem, meaning it could be approached using programming languages to approximate or even find an optimal solution for the game. We have demonstrated that for finite cases, the Kelly criterion is not necessarily the optimal solution for Jack Tong's challenge. However, it can serve as a reasonable approach when the rounds of the game are large. To bridge the gap between n equal to 1 and n tend to infinity, we explore the use of Kelly criterion. In the following simulation, Party A invests based on the Kelly criterion, while Party B employs other strategies. The winning probabilities and odds, as mentioned earlier in this presentation, are generated using Python. The results of this simulation will be presented in the following 2 slides. On this slide, we present the simulation results, where Party A follows the Kelly criterion and Party B invests uniformly on the interval 0 to 1. Using the previously described winning probability and odds, the winning time, as shown in the graph, represents Party A's winning time. As the number of rounds in the game increases, we observe that the Kelly criterion begins to dominate. This shows its strength as a strategy that leverages information about winning probabilities and odds, optimizing decisions over repeated rounds. In contrast, Party B's uniform investing lacks such adaptivity, highlighting the effectiveness of the Kelly criterion in long-term decision-making scenarios. Let's take another look at the simulation results for different strategies. In this scenario, Party A is investing using the Kelly criterion, while Party B is investing uniformly within the range 0.65 to 1. The graph shows the number of wins achieved by Party A across 100,000 simulations as the number of rounds increases. As we can observe, Party A performance improves significantly when the rounds of the game are more. These results highlight the strength of the Kelly criterion in repeated investing scenario. Over time, a more calculated strategy, like the Kelly criterion, consistently outperforms random approaches, even when the initial conditions are similar. To conclude this presentation, let's summarize what we have achieved throughout exploration of Jack Tong's challenge. These findings encapsulate the key theoretical insights and practical implication of this work. Theorem 1. First, we show that when n equal to 1, the optimal strategy for both parties with the same probability of success, P, and odds, B, is determined solely by the value of P in Jack Tong's challenge. This simple yet important case highlights the significance of the probability of success in decision-making in a game with only one round. Theorem 2. Next, we demonstrate that as n tends to infinity, the Kelly criterion emerges as the optimal strategy for both parties with no additional information is available. Here, we connected the Kelly criterion to Jack Tong's challenge, showing that it emerges as the best approach under these conditions. This highlights the robustness and adaptivity of the Kelly criterion as a tool for long-term decision-making. Example 3.1. Then, we explore the complexity introduced when n is finite and n not equal to 1. In this scenario, the dynamic of reasonable solutions resemble a rock-paper-scissors-like game, where strategy interacts cyclically. This raises deeper questions about whether a truly optimal solution exists for such non-trivial cases. And for those non-trivial cases, besides proving the optimal case for general non-trivial cases, it might also be a great computational game theory question that professors in computer science or mathematical economics departments could challenge their students to simulate and submit their code. We also demonstrate that as the number of rounds in the game increases, the performance of the Kelly criterion improves. This result reinforces its strength as a strategy optimized for repeated decision-making, particularly when one knows the real probabilities and odds. Finally, and most importantly, we propose what may be one of the simplest models for addressing decision-making in winner-take-all competition frameworks. This connects our theoretical findings to broader real-world applications. In summary, Jack Tong's challenge not only provides theoretical clarity about optimal strategies, but also serves as a framework to analyze decision-making in variety of competitive contexts. This work paved the way for future exploration of strategic interactions under uncertainty. Thank you for your time and interest in the project. Before I concluded, I would like to take a moment to express my gratitude. First, I sincerely thank all the professors at Emporia State University. Without your support and guidance, I wouldn't have the opportunity to explore this concept in such detail. Additionally, I would like to thank my friend Harry from UC Davis for confirming that the alternative strategy outperforms the claimed optimal strategy in example 3.1. Your insights were invaluable in refining this work.